Okay, so now we're going to start probably the most important chapter in this entire class, and that is control volume analysis. And to a certain extent, you've done a bit of this in thermodynamics, but in this class, as I said earlier, we are going to be formalizing this theory a lot more than we did before in thermo. And this is control volume analysis, and you will often see these equations that we're going to work with referred to as the integral form of the governing equations. And the reason they're called the integral form will become clear later on. So in your earlier classes, such as dynamics and thermo, you studied basic conservation laws. Okay, and these were given, and they were often for a rigid particle. In fact, that's how the basic conservation laws are written. So basically what they are is if we have this goofy potato-shaped particle, we would follow the particle around and you would apply the various conservation laws to that particle. And we had conservation of mass. And conservation of mass says that the time rate change of mass in the system, which I'm going to define as in this little potato-shaped volume, is constant or equal to 0. And then mass, if the density is varying, is just equal to the volume integral of density times dv. Okay, and so if you wanted to basically what this law says, if we're following this particle around, it doesn't matter where it is; its mass is not going to change. Okay, and now the other law that you dealt with quite a bit in dynamics, and that is Newton's second law, or a balance of momentum, and that says that the time rate change of momentum is equal to the sum of the external forces, and so the vector of momentum is just mass times the velocity, and the momentum in this volume is just the integral then of rho times the velocity dv over the volume. Okay, so you could apply Newton's second law if there was some sort of external force pushing on this. If there was some sort of external force pushing on this, we could then calculate the motion of this object. Then in thermo, you dealt with the first law. Okay, with the first law of thermo, and that stated that that the time rate change of energy in the system is equal to the heat going in and the work going out. Or in a different way, we'd have dE equals delta Q minus delta W, where again, recall from the first pop quiz that these deltas refer to inexact differentials that are path dependent. The D's do not depend on how you get from state 1 to state 2. The deltas do. Okay, and I already have that right here. And here in this class, I will define the internal energy or the energy as E, not U, so it's not confused with the x component of the velocity. And so that's just that's just mass times the internal energy, or mass times the energy per unit mass, which would be mass times the internal energy plus the kinetic energy plus the potential energy, and that's equal to the volume integral of rho E dV. Okay. Then there's everybody's favorite law, and that is the second law of thermodynamics. And the second law states that the change of entropy is greater than or equal to delta Q over T, or in rate form, that ds dt is greater for the system in this little potato thing is greater than or equal to the the rate of heat transfer divided by the temperature of the system. Okay, and then also we can conserve angular momentum. We can do all sorts of things. Now the problem is is that all of these conservation laws are written as if we're chasing this, as if we're chasing this particle around, and that's called a Lagrangian frame of reference. Okay, so that's called a Lagrangian frame of reference, where we basically follow particles around. And this is difficult for fluids because, as I've sort of argued earlier, that fluids, you could imagine, are made of many different individual fluid particles, and they deform, and you have to chase all of them around, not one or two of them. You have to chase thousands upon thousands upon thousands upon thousands of them around. And that's not really useful or even practical. Okay, and so it is often more convenient to apply these conservation laws in an Eulerian frame of reference. And what an Eulerian frame of reference means is a control volume. Okay, and so, for example, we could say we could consider a rocket, and say we are interested. So we have a rocket here, and we want to calculate the thrust of this rocket. So basically, how do we do that? Well, in the Lagrangian frame of reference, you would basically follow all of these little molecules or fluid particles around and calculate their net momentum change. And then you'd apply Newton's second law to each and every single little particle, and then you could apply Newton's third law that an action has an equal and opposite reaction. That is, if these fluid particles are accelerating outwards, and if you can count all of them up to get the total amount of momentum of particles leaving, then you can get the change of momentum of the object confining them. Okay, but that's not practical. You have to count up a whole lot of these things, and that's not very useful. And so the other way that you could do this is, well, you could draw a little control volume around the surface, and if you knew the pressure field that is basically pushing on it everywhere, and you know that in the rocket, intuitively there's going to be high pressure inside and lower pressure outside. Well, you know that there is going to be high pressure pushing this way here, and the pressure pushing from the outside is going to be less than that. So on the shell of the rocket, there's going to be a net force that is pushing it to the left. So in theory, you could find the thrust of this rocket by just integrating the pressure forces on the surface of this on the surface of the shell of the rocket. But unfortunately, to use that, you need to know the entire pressure field on the entire surface of the rocket, and you need to do a surface integral, a very complicated one. And that's not easy. And now a third alternative, which is related to this one, is, well, what if rather than counting individual molecules that are leaving the rocket to find their effect, what if we just did a control volume much like you did in thermodynamics? Okay? And then you calculated the momentum leaving, the momentum of the fluid leaving the rocket, and thereby you can then use Newton's second law and compute the thrust. But now the issue is Newton's second law is written for a fluid particle. So it is written for a Lagrangian frame of reference. So how do we take this Newton's second law and convert it into a form that is useful and suitable for a control volume? Okay? So, and so basically we will get to that here in a bit. And so if we're to do this in the Lagrangian frame of reference, you can just sum up F equals d, the sum of all the change of momentum of all these little fluid particles. And as I argued earlier, you need a whole lot of them to get a good calculation. And there's really way too many of them to use this so-called Lagrangian frame of reference. Okay? But you don't need to know the entire pressure field, which is an advantage of that approach. And so now, as I argued earlier, we sort of want to look at a control volume. And by a control volume, that means instead we are looking at a fixed window. And we keep track in that fixed window, or a control volume, of the net mass, momentum, energy, entropy, etc., that are basically entering, leaving, and possibly accumulating. Okay? And so, but now, how do we apply the basic conservation laws for a system that is in a Lagrangian frame of reference, where we're basically following them around, to a control volume form, which is an Eulerian approach? Well, how we do that is by, probably in terms of fluid mechanics, one of the most important mathematical theorems there is, and that's the Reynolds transport theorem. Okay, and I'm going to call that the RTT. And what the Reynolds transport theorem does is it converts conservation laws from a system to a control volume form. Okay, and so what we're going to do is we're going to show what it is for a generic one. Then I will derive it. So here we're going to consider a system, and so we have a system here, and it contains some quantity n, and n is the same n that I showed in the previous video, and basically the amount of n in this little differential cube is just equal to basically rho times eta times dv, the same eta as last time. Okay, and then the total amount of n in our system is just equal to the entire volume integral. And now all conservation laws, why we care about keeping track of the amount of some sort of arbitrary quantity cap n, is that all conservation laws have a time rate change of something with respect to time is equal to something. This something can be zero in the case of conservation of mass, or it can be the sum of forces in the case of Newton's second law. So now we actually want to sort of convert these things. And so in this class, we will consider n being mass, momentum, and energy. We won't deal with entropy, which probably make a lot of you happy, and we will not deal with angular momentum. If you guys take a course in turbo machinery or gas turbines, you will be dealing with that form of it. Okay, and so now n cis is the total amount of the property n in our system. Okay, and that is an intensive property, or that is an extensive property, and that is it depends on the size or the extent of the system. And so, for example, if density is constant, if you double the volume, the mass will also double or go up. And so the mass depends on basically how big this volume is. Okay? In general. Now, intensive properties, which is eta, are usually properties per unit mass, and they are intensive, and they do not depend on the size of the system. So that is, eta can be density or velocity or temperature or pressure or internal energy, and those do not depend on the size of the density does not depend on the size of the system. It's just a property of where you are in the system and time. Okay, and so now, how do we find n? I kind of did this in the last video, but it bears repeating. So let's look at the definition of mass. Well, the mass in the system is just equal to the volume integral of rho dv. And, well, our property n is defined to be defined to be the volume integral of eta times rho dv, and we have that mass is defined to be the volume integral of rho dv. And if we want to equate these two integrals, it's clear that we choose eta to be 1 for mass. Okay. Now, how about momentum? Well, momentum is just mass times the velocity, and that's given by the volume integral of rho times velocity dv. And so the total amount of momentum in the system is given by this volume integral here. And we want to find an eta here that basically makes this true. Well, we have a rho here, a v here, and an eta there. And you can see that just by inspection that these two integrals here are the same if we choose eta to be equal to the velocity. Okay, and I can go forward for a whole lot of these things. The angular momentum, internal or total energy, entropy, etc. Okay, essentially all of these conservation laws have something in common. They have some quantity times density, are like say rho times E, rho times entropy per unit mass, etc. And so that quantity that is multiplied by rho is basically eta for basically all of these things. Okay, so and there are other things that you can conserve too that we're not going to go over in this class. But in summary, the total amount of something n in the system is defined to be the volume integral of eta times rho dv. And I showed this table. I showed this table before, and I'm not going to go through it in detail. But this is just a sort of a tabular form of the statement that I just made above. Now, the Reynolds transport theorem, or the RTT, states that for a stationary control volume, and we are going to generalize it to a deforming control volume and an accelerating control volume. The RTT states that for this control volume here, this is a generic control volume. So the volume is called the control volume, which I will call CV as the control volume. And we have to identify the surface of the control volume with a dashed line. You guys did that in Thermo. And that's called the control surface. And it's really just the surface of the control volume. And at each point on the surface, we can have some n hat. And we can have some amount of n leaving that surface. So that could be v times eta times rho. Or you can have v crossing it, all sorts of things. And so now, what the Reynolds transport theorem states, and we're going to derive it here, a very hand-wavy derivation. What the Reynolds transport theorem states is that if we want to conserve n in the system, what you need to do is the time rate change of n in the system, and I apologize for using cap dn, cap dt. This notation will become clear later on in class when we get to chapter 5 or 6. Okay, what basically what the Reynolds transport theorem states is that in the conservation laws, I'm going to scooch back up now. all of these conservation laws have the time rate change of something is equal to something. And so what the Reynolds transport theorem does is it converts this time derivative into a form that is useful for a control volume. And then it does not say anything about the right-hand side of these conservation laws. Is you still need to figure out we still need to figure out like what to do with those. But now it converts this time derivative following the system to a time derivative that is applicable to this control volume. And that time derivative of the system is equivalent to partial t of the volume integral inside of the control volume of eta times rho dv plus the surface integral of eta rho v dot n hat dA. And now this symbol here, note that this symbol here, that an integral with the surface, this means it is a closed surface or closed volume, and or closed volume. Okay, and so for to use the RTT, the control volume, it must be completely enclosed. You is that you cannot choose your control volume to be over just a small fraction of the surface. It needs to surround the entirety of the surface. Okay, and so if we are integrating in something over the entirety of the control volume, that will be given by the symbol CV here and a dV here. And if we are integrating over the entirety of the surface, that will be given by a CS over here, and we'll be integrating over the area. Okay, and so this cap dn cap dt is the time rate change of n in the system, and this n in turn is based on the conservation principle for a particle. Okay, and this first term here in the RTT is the accumulation of n inside of the control volume. Like you could imagine your control volume is a balloon, and you keep filling it with air. So that'd be like a tank filling, like mass in a tank filling problem. And this term here is the net flow or flux really of n out through the control surface. Okay, and we will have almost countless examples of how to use this in the coming lectures. Okay, and so now we need this. This sort of Reynolds transport theorem looks kind of abstract and vague, and I know these volume and surface integrals look intimidating, but after you get used to them, they will become your friends. Okay, and now the derivation. This is a pretty hand-wavy derivation. There's a mathematically rigorous one that is extremely intense, and we're not going to do that in this class. Unless you want to keep track of metric deformation tensors. And I don't think you guys want to do that. So here, we are going to consider a moving system and a stationary control volume. This analysis can easily be upgraded to a moving and deforming control volume, but for the purposes of derivation, I will derive it for a stationary control volume due to simplicity, and then I will just more or less state the results for a deforming control volume. And now we're going to be kind of clever with this, is that really what we want to do for a Reynolds transport theorem is state the time rate change of something in the system, and and find the equivalent for a control volume. So essentially what we're going to do is we're going to choose a control volume and a system and follow the system around and keep track of what's going in and out of the control volume as the system moves. And so we will consider that at time t equals some t naught, the system and control volume are in the exact same position with the exact same shape. Okay, so I have one sketched down here. So I've drawn the system boundary here in brown. And we have the control volume here in the dashed line. And the control volume is the boundary of the control volume is supposed to exactly match the surface the control surface of the control volume is defined to match exactly the surface of the control system. And recall that the control system, it is moving with the flow, and we are defining the control volume in the dashed line to basically stay put. And so now what we're going to do is we are going to basically let the system move for a time delta t, and then keep track of what moved with what basically moved with the system, and then basically see what that says. Okay, and so at later times, the system will basically move with the flow, and let's keep track of the amount of n inside of the control volume. Okay, and so we can draw the same picture at time equals to t naught plus delta t. And now our control volume stayed put. That is right here. And our system moved with the flow. So it moved to the right just a little bit. Okay. And so the control volume, which is in the dashed line, is fixed, and the control system is moving. And notice here now that we essentially have three different regions. We have this sort of red region here, and this red region, I'm going to call that region 2. And basically this region 2 is material that is inside of both the control volume and in the system at time equals to t plus delta t. Okay, and so basically that means the system has not completely left the control volume yet. There's still some of the original material that is inside both the control volume and the control system. Okay, and notice we have this blue region here. This blue region is material that is in the system, but it is no longer in the control volume. I will call that region 3. Okay, and so this region 3 is some material that is no longer in the control volume, but is still in the control surface. Okay, and again, I reiterate that the control volume is fixed in space, and the system has moved. Okay, and now we also have a third green region, and I will call that region 1. And in this region 1, this is material that is in the control volume, but is not in the system. Basically, you could imagine that that our system is basically moving, right? And basically, as it moves, there is going to be some material that will basically backfill in behind it, and that's basically what region 1 is. It is the material that has entered the control volume that is backfilling the void left by our system moving it. Okay, And now what we are going to do is we now have the amount of n at t equals t naught for both the system and the control volume. They are actually one and the same. So at time t naught, the control system, which is the brown line, and the control volume are the same. And we know then that the amount of n in both the system at time t naught and the control volume are the same. And so that is the amount of stuff is the same in between them because we've defined them to be identical. Okay, but now that's not the same at time equals t naught plus delta t. Okay, and so at that time, the stuff in the system, after the control surface has moved, is basically shifted to the right, the stuff in the system is equal to the stuff in this region 2 plus the stuff in this region 3. And so that is the stuff in the control the stuff in the control system. Okay, so the stuff in the system is equal to the amount of material in the red region plus the amount of material in the blue region. And then the stuff in the control volume, which is right here, is equal to the stuff in the red region, that is in region 2, and the stuff in the green region, which is region 1. Okay. So we can play some games and we can solve for N2 in terms of the amount of material in region 2, or the red region. That is equal to the amount of material in region 1, and that is subtracted from the amount of material that is in the control volume. Okay. Okay, and so you could consider the amount in the control volume at t naught plus delta t is just this entire thing right here. Okay. Now, so we now know the amount of material in basically all of these different sections at different times. And so now we actually want to compute this derivative here. So let's use the definition of derivative. And we want the time rate change of amount of n in the system. And that's equal to, we're going to use the definition of derivative. That's equal to the limit as delta t goes to 0 of the amount of stuff in the system at time t plus delta t minus the stuff in the system at time t naught divided by delta t. Okay. So now we know what this is, and so now we basically need to relate the stuff in the system to the stuff that is in the control volume and in these three different regions here. Okay? and by relating the amount of stuff in the system at these two different times to the amount of stuff in the control volume, we have a time rate change of stuff in the system will be equal to the time rate change of stuff in the control volume. Okay? And it does not look like it, but it does not look like we are going to get some area integrals, but we are. Okay? So we can simplify this. Well, but at time t naught, the amount of material in the system is equal to the amount of material in the control volume, so we can just replace that directly. And at time t naught plus delta t, the amount of material in the system is equal to the amount of material in region 2 plus the amount of material in region 3, as I've derived above, and we have n through this expression here. We have we basically want to eliminate. We actually want to we actually want to turn this into terms of the amount of material in the control volume. So we'll just basically solve this relation here for the amount of material in region 2, and that's the amount of material in the control volume minus the amount of material in region 1. So we have that the amount of material in the system at a time t0 plus delta t is equal to the amount of material in the control volume at t0 plus delta t minus the amount of material in region 1 plus the amount of material in region 3. Okay, so looks like we've made a bit of a mess of this, but we can simplify this a bit, and we find that this is just the definition of derivative, as I said before, and we can make these substitutions here for the amount of material in the system at 2 different times, and then when we substitute that in, we get this expression here. So we have our NCV at t0 plus delta t minus the amount in region 1 plus the amount in region 3 minus the amount of material in the control volume at time t0. Well, I'm going to do some light rearranging here. I'm going to take these two terms here and put them together. And so this equals to the limit of NCV at t0 plus delta t minus NCV at time t0 plus the amount of material in region 3 divided by delta t minus the amount of material in region 1 divided by delta t. And here you can see that this is, by definition of derivative, this here is the time derivative of the amount of stuff in the control volume with respect to time. And if we note that the amount of stuff in the control volume is cap n, and cap n is the volume integral of eta rho dv, we have this term here. And so now we have one of the 2 terms in the Reynolds transport theorem. And now we have these pesky terms here. So what do we do with these? How do we relate these to the control volume or the control surface? So what do we do with those? Well, let's just sort of think about this for a little bit. And let's find the amount of n in region 3. And so first we will zoom in on region 3. Okay, and so this here is an extreme zoom in. So this is this here is basically an extreme zoom in of essentially this region here. Okay, and so we are way zoomed in. So we got the streamlines of the flow that the control surface, or that the control system, is moving with. This here is region 3. This here is the right boundary of the control of the system, and this here is the right boundary of the control volume. Okay, and so really what we need to do is to find the amount of n that is in this region here. Okay, and then essentially what I'm going to what we can do here is we can basically think of this as, well, we have stuff in the system that has basically moved through the surface. Okay, and so we can basically define a small differential area right here. So I'll just draw a little dA over here. So we'll have a little differential patch. we have n hat pointing to the right, and we have some velocity vector v. Okay, and this is an area element dA. And so if I really want to, and so what I can do then is find the amount of material that has moved through this small dA between time t naught plus delta t and time t naught. And it turns out that that is the amount of material in this yellow shaded region here. Okay? And so this here is material in the system that left the control volume. And so what is the amount of n in the small little in the small little area? And I will make a little note here and state that note, these are streamlines. Flow does not cross the streamlines, and so basically all material in this region here had to go through this small differential area because it is bounded by the streamlines. Okay, and so basically the mass. So if this, do I have a brown one? No, I don't. So if the system again started here and moved this way, this here is basically mass that basically started over here, and then basically shifted to the right. Okay, and if you recall, our molecules in a pipe that we did in the previous video, it is the exact same argument as that molecule in a pipe argument. Okay, and so basically we just need to find the flow rate of n through this dA. Okay, and that is just the flow through a surface. Okay, and so the flow rate of n through our dA is, I'll call that dn dot of 3, or dn dot of region 3, and that is equal to, as we derived last time, as eta times rho v dot n hat times dA, and then we basically integrate. We have a differential patch here, a differential patch here, a small differential patch here, a different, and so on and so forth. And so we basically integrate over the entire surface to find a total flow rate of basically n through the surface at any given time. And now note that we are using this for a very small delta t, because it is going into the definition of a derivative where we're going to take the limit as delta t goes to 0. So if delta t is essentially small, it's approaching 0 but not quite 0, then we can easily argue that if delta t is small, then during that small delta t, this flow rate of n crossing through the surface is essentially constant. So thus, this implies that the amount of material in region 3 is just delta t times the total flow rate of n through that surface. So that is just given by delta t times the area integral of eta rho v dot n hat, basically times dA. And then basically what this means is this here is the control surface out, and it is the control surface of material that it is the portion of the control surface of material that is leaving the control volume as it follows the system. Okay? And note, I do not have the circle here because it is only a portion of the surface. It is not a closed surface. Okay? And so now we have basically argued what the amount in region 3 is. And note that, again, this is the same argument. This is very similar to the argument that we made as the molecules in a pipe. In fact, I could derive the exact same thing, doing the exact same argument by basically saying, well, there were a bunch of molecules here, and then we basically followed them through the surface. We basically followed them and then counted them as they flowed through the surface. It's the exact same argument. Okay. Now we got to do the same thing with say region 1, and I'm not going to go through that one in detail. It's largely the same as it was for region 3, and so that surface is largely the same, except for, again, we have streamlines going this way here, and the surface moved to the right, and so this region 1 is basically, as I said earlier, it is material that basically filled in the void as the system left. Okay, this is material that has not left the control volume, it has entered the control volume. Okay, and so we could apply the exact same argument, and what you would wind up with is that the amount of material in region 1 is basically delta t, or is basically minus delta t times the surface integral over this surface here, and only that portion of the surface there, of eta rho v dot n hat times dA, and that's the exact same procedure. And now note, there is one difference, that I have a negative sign here. And how I got that negative sign is that basically n hat points to the right. Or I mean, it points to the left, and I will after I show you the proper definition of n hat, we will basically find that in this case v is basically following the system, right? And so v is going to the right, and n hat is pointing outside of the surface, and that's pointing to the left. And so basically v dot n hat are in opposite directions, and so there's a negative sign here. Okay, and so and that basically means if it's negative, that means if this is negative, that means that it is filling the control volume. Okay, and I will make a small note, but you can go through the exact same procedure as we did for region 3. You can get this result. You just have to note that there will be a negative sign there because the material is basically filling it. And it may seem kind of opaque to you now, but as you use the result of the RTT for conservation of mass and momentum, we'll spend at least 2 weeks on this. You will get lots of experience with that, and it will become like second nature to you. Okay, and then note there is a portion of the control surface that we did not include, and those are the quote unquote sides. They have no contribution. Okay, and so we could draw a picture here, and these sides here are basically parallel to the flow. And essentially that means that v dot n hat is 0 on the quote unquote sides. Okay? Which implies that the area integral over these side regions is equal to 0. However, we do need to include these because we need a surface integral over the entire area and not just a portion of it. Okay, so now we know the amount of material in region 3 and the amount of material in region 1. We can basically use those results and we can put everything together. So putting everything together, we have, from our previous result, we had the time rate change of the amount in the system is equal to the time rate change of the amount of n in the control volume plus the limit as delta t approaches to 0 of the amount of material in region 3 divided by delta t minus the amount of material in region 1 divided by delta t. And we use these results up here and substitute them in. And you get, again, the time derivative of the amount of n in the control volume plus the amount in region 3 minus the amount in region 1. Plus, we need to control, so basically, region 3 gets us this surface here. Region 1 gets us basically this surface here, and we still need to completely enclose the volume. So we need basically these sides here, and so I will add those as 0. They have no contribution; they're not changing the result. But if we're being strictly mathematically rigorous, we do need to close the we do need to close the volume. But notice that this here is just nothing more than the surface integral of over the entire surface, because basically this minus sign here will be because we have minus minus, this turns to a plus, and so we have an integral of rho eta v dot n hat over like this surface here and this surface here and the sides. So notice that we have completely enclosed the entire volume, and so the sum of these three integrals is just the surface integral of rho eta v dot n hat dA over the entire control surface. So finally, we have done a hand-wavy derivation of the Reynolds transport theorem. Okay, and so this is the RTT for a stationary, non-deforming control volume. Okay, so now one thing that I will, this caused a bit of confusion last semester, so I can hopefully clear this up before we get going, is that these, to do the surface integrals, we need to know what n hat is. And so how do we pick that? Okay, and you may think, well, n hat, that should be obvious, it just sticks out from the surface. Okay, but how do we define out? Okay, so say I have a control surface here. How do we pick n hat? And if I'm, say, pick a point there, it is slightly ambiguous. I could choose n hat going to, that is basically pointing down, or I could pick n hat that is pointing up. They are both qualified n hats. So basically, which of these two n hats do I pick? And this is our control volume. Okay, so which one do I pick? Well, there are some rules for picking that, and this will become like second nature to you. And for all the examples that I've given, and then when I did the flux through a surface, I instinctively did this. So as you guys get used to this, you will just instinctively know how to pick n hat. Okay, and so the rule, or the sort of procedure is step one is you kind of walk along the boundary, and you walk along it counterclockwise. Okay, so that means you would start here and you would go in a counterclockwise direction. Okay, and so, and if you are the one personally doing the walking, so, and you are walking around it counterclockwise, you basically set it up so that basically half of your body is on one side of the line, and half your body is on the other side of your line, or is on the other side of the line. And so if I'm in this region here, I can draw a little stick figure. Basically, half your body is on this side and half your body is on this side. And let's see, I'll redraw the face a little bit bigger. And so notice that basically they are moving down. So on this side they are facing you. And so their left leg is so the side of the surface that their left leg is on is defined to be inside of the control volume, or it should be inside of the control volume, and their right leg will be outside of the control volume. Okay, and then n hat points towards the outside, and so that basically means that basically n hat points. It basically points to your right. Okay, and n hat points outside of the. It basically points outside of the control surface. Okay, and so if you were to put the stick figure here, they look like that, and their nose would basically be they would be facing this way, and their right would be pointing in this downward direction here. Okay, and so that means that n hat is this one right here. Okay, so basically the sort of rule of thumb is basically just walk around the surface in a counterclockwise direction, and basically outside is defined to be on your right, and then hat always points outside. Okay, and so that's the RTT, and in the next lecture we will be applying the RTT to conservation of mass.